Okay, so what I was explaining. Let me start the start. Fine. Thank you. Where I stop. Okay. So C1 means when transistor is in off. Okay, there are two capacitor between gate and depletion. C1 means gate to channel. C2 means channel to depletion layer. Okay, so that is different types of capacitor structure I mentioned C1, C2. Similarly, C3, C4. Okay, so C3, C4 means overlap capacitance. So you remember, particularly channel length, how we are defining. Okay, let me explain here. What is the ideal thing? P substrate. Okay, N plus N plus. Okay, here only channel is there. So this is channel length. So what about gate? This is oxide layer. This is a gate. But you can see below the gate only the channel is there. But practically what happened? There will be channel overlapping will be there. That means practically after fabrication. Okay, so you can see the gate will come. So now you can see here ideally L, but practically L will be reduced by this overlapping. Let us overlap is del L. So L actual channel L minus del L. So this is called as L dash. So this is some overlapping. Channel length overlap with the gate. Okay, so it will introduce some capacitance. Ideally, there is no capacitance between the source and this thing, but due to overlapping, this overlapping length will introduce the capacitance with the source and drain. So this is drain, this is source. This is called as overlap capacitance. CGS, that means gate to source overlap capacitance, gate to drain overlap capacitance. So why that overlap happens? Because channel is overlapping with the distinct. Is it clear what I am saying? Okay, so that capacitance on C3 and C4. Similarly, that C5, C6, these are depletion capacitance. Depletion means what? P-N junction depletion. You can see N plus P substrate, depletion capacitance. These are, P substrate always connected to ground. So these two P-N junctions are in a reverse bias. Reverse bias means depletion capacitance. Right? Or simply junction capacitance. You can see this is a junction capacitance. C5 and C6. Right? So this is depletion one. You can see this is I am saying in a vertically top view. But you can see there is some side portion also there. So due to side portion, there is some side wall capacity. Right? Ideally, junction capacity, there is some side wall capacity. Okay, so in when you study MOSFET testing, so only these kind of capacitance will come. Either depletion capacitance, overlap capacitance C3, C4, and the capacitance between the gate and depletion. That means between gate and the channel, channel to the depletion. That means simply gate to bulk. Is it clear? Different types of capacitance. Any doubts here?
No,
Oh,
sir.
any doubt? Thank you. So any doubt you can ask me. No issues. Okay. So first we'll so after understanding what are the different things, now we'll come to represent in terms of equation. First we'll start from C1. What is C1? Okay, gate is there, oxide layer there. This is a gate, then channel. This is a channel. So this is a oxide layer. So what is this capacitance called as? This is a C1. Second capacitance there. So what is this between oxide layer there? So this capacitance called as oxide capacitance. So WL Okay, Cox in per unit area. You might have studied in the STC. So Cox into WL. WL is the area. So C1 is WL Okay, so what is C2? C2 I already mentioned. It is capacitance between channel to the depletion. It is a depletion capacitance in the MOSFET, not in a PN junction. Depletion capacitance in the MOSFET. So we might have studied this formula in device physics, might have derived this thing. So this is a depletion capacitance. So I will underline here. Depletion capacitance between channel and substrate in the MOSFET. Not in the PN junction. PN junction depletion capacitance different. MOSFET channel depletion capacitance different. Because MOSFET depletion capacitance formed by the channel and the substrate. Right? So channel and the substrate. So that's what depletion layer. So that formula, please refer your STC course. Okay, so that is C1, C2 formula. Now we'll come to overlap, C3, C4. So what is C3, C4 is happening due to overlapping. So what is the overlapping length? L overlap. So simply W, there are also oxide layer there, some small. So W, Cr. So in terms of L, overlap length, L overlap. Okay, so practically, instead of using, people represent this W, L overlap here, they will simply put C overlap. It is become a device parameter. Because L overlap device parameter, C is a device parameter. Simply these two things they will represent as a C overlap. So what is overlap capacitance? W into C overlap. So this is C3, C4 equal to. So where C overlap is L overlap length into CR. Okay, so when you take that model library, they will specify by this only. They will not specify the overlay length. Directly they mention C overlay. That means it intrinsically means the diffuse length into oxide capacitance. Right. So that's about overlap capacitance C3 and C4. So you finish C1, C2, C3, C4. So what are remaining? Depletion capacitance. What is depletion capacitance? PN junction depletion capacitance. So anyone of you know the formula for PN junction depletion capacitance? How it might be?
Epsilon A by W.
How it might be? Okay. When I'm increasing the bias voltage, what about capacitance? Okay, let's take PN junction. PN junction. Okay, so this is a depletion with. Right? So PN junction, I am applying reverse bias. Let's take VR. So here actually the capacitance. Okay, depletion capacitance. Increasing VR, depletion capacitance will increase or decrease.
Increase.
Decrease. Okay, so you need to remember that thing. So the formula is PJO divided by root of 1 plus VR by 5B. 5B is a built-in potential. Okay, VR is a applied voltage. That's all. So you need to remember increasing thing, it will reduce the capacitance thing. Okay, what is a built-in potential? It will be around 0.3 to 0.4. Okay, so that's all about CJ. So I discussed about CJSW also. That will be specified in the device model. So no need to remember the formula. So the actual depletion capacitance is CJ plus sidewall capacitance. Ideally CJ, but non-ideally some sidewall also there. Some that capacitance. So that small signal model tool will consider this capacitance also. So now, so this is a layout for the MOS transistor. So I will not cover the thing now. Okay, it will that otherwise the things that we are learning now, it will become complicated. So maybe after CAT 2 we'll discuss about layout. At that time I will discuss this thing because I don't want to put too much learning now itself. Okay, we'll skip this slide. That's no. Okay, we'll just learn the basics. So when you come to layout, how the layout will helpful to reduce the capacitances at the time we will discuss. Because with that foundation, it will be will clearly understand what is the fingering and that. Okay, so don't worry now. When you go to the maybe when you go studying about amplifier at the time I may explain if it is required, but it is not required now time being because we are concentrating on small signal modeling. What are the capacitances and the formula? Now we'll come to the. So now we understand what are the different capacitors. What is C1 means WLCR. What is C2? C2 is a depletion capacitance of the MOSFET. What is the formula? Similarly, junction capacitance formula and overlap capacitance formula. Okay. So now we will come to MOSFET in the different operating region. What are the different operating region of MOSFET? First off condition, then on condition. On condition means triode and saturation. So in off condition, what is the capacitance inside the MOSFET? In triode region, what are the capacitance will come in the MOSFET equivalent circuit? Similarly, in saturation region, what are the capacitance will come into picture? So first we'll start from the MOSFET is off. Okay, so let me draw the off means don't think like there is no inversion. It is off means VGS less than VTS. You need to think like this. Okay. So anyone can answer whatever capacitance might be there. Whatever capacitance might be there. First, whether C1, C2 there, that means gate to bulk. Any capacitance there?
C1 is present, sir. Oxide capacitance.
C1, C2. So gate to bulk, C1 will be there. Okay, C1 will be there. C2 will be there. Okay, so what is the equivalent thing? C1, C2 are in series. Series means how can I write?
C1
C2
C2 by C1 plus C2.
C1, okay, C1 inverse, so C2 inverse. Okay, so that's the thing. So between gate to bulk, right? So C1 and C2 there. Okay, so C2 is a depletion capacitance. So where C2 is a depletion capacitance, what is C1? C1 you just know the oxide capacitance, WLCX. Okay, that's what WLCX CD. This thing, this formula. Right. So C1, C2 over. Now we'll come to whether any overlap capacitance there. C3, C4. Definitely there. Am I correct? Okay, so what is the formula? This is C3, C4. This is the formula. What about depletion capacitance? It is there or not?
Yes, sir.
Depletion capacitance always there. Right? So the depletion capacitance, CSP and CD. Okay, that will vary, depends on the applied voltage. Inversely, root proportional, but inversely proportional. So remember,
Sir,
formula. Okay, so now we finished off condition. What are the different capacitance in the off condition? Okay,
sir,
this curve I will explain later. Yes.
sir, in off condition, the channel is not fully formed, so
No.
the overall
Channel is there. That's what I don't know. Small number of electrons there. Channel not sufficiently to turn on.
okay, sir. For that weak inversion, also the overlap capacitance will be considered.
Yeah. Because it will come like that, no?
Okay, sir.
Fine. So now I want to teach some basic. Fine. So metal, oxide, okay. Now I remove it. P subset, metal oxide semiconductor, MOS. Now let's assume I don't have source and drain. I don't have source and drain. So with this, whether inversion layer is formed, you remember in device physics, without source and drain only you studied about inversion layer. Am I correct?
Yes, sir.
Yes, sir.
So inversion layer is formed. Okay, so if I apply more and more gate voltage, who will supply the electron for inversion layer? Either from the substrate or from source and drain?
Substrate.
No. Up to
From
forming the inversion layer only P substrate. After that, source and drain will come into picture. That's what this is called as source of electrons. Substrate won't that much. Substrate will come of just forming the inversion layer. After that, source will come into picture. It will become much. It will supply more number of electrons. That's what in device physics, when you start inversion layer, you will not study source and drain. When you derive the current expression only, you will come here. When the current will come, VGS greater than VTS. Am I correct? That means defaultly some inversion layer is there. Is it understandable? What I'm saying. Some channel will be there. So you always remember in PN junction, I am not giving any supply voltage. Is there any depletion agent there?
Yes, sir.
I'm not giving any supply thing.
Yes,
Whether
sir.
there is any depletion agent in PN?
Yes, sir.
Definitely
Little
there.
bit.
Because electron there, more holes are there. Okay, it will try to diffuse. That's diffusion will form the depletion agent. That's what intrinsic built-in potential. Without giving the supply voltage, there is some built-in potential. 0.7 volt. Once you like that, can assume intrinsically some channel that is not sufficient to turn on the transistor. That can be done only by the source. That's what VGS later than VDS. Source will come into picture. I hope you understand. So that's what the channel capacitance there. Now it's understandable why the channel capacitance coming. Okay, so that is in off condition. Okay, so now you can see off condition. Okay, so CGS is overlap. So this curve is CGS. This curve is CGD. Okay, so CGS equal to CGD because there is no channel. So source and drain, we can say both are same. Right? So CGS equal to both are only that overlap capacitance. Right? Sorry, I'm sorry. CGD only overlap capacitance, but source you can see. Just 1 minute. I'm missing something here. So there will be gate to bulk only C1, C2. This is gate to bulk, but CGS, CDD only overlap capacitance because you can see overlap here. Okay, so only overlap CGS, CDD only overlap capacitance. Gate to bulk only C1, C2, that parallel formula. Okay, so now we'll come to device is turned on. Okay, so VGS greater than VTS. Okay, so now I am drawing the structure now. Okay, first thing is here inversion layer is formed. Fine. So now inversion layer is formed, so there won't be no gate to bulk capacitance. So only the gate to this channel capacitance only will be there. Now you can see channel is uniformly distributed. Okay, so channel is uniformly distributed. So you can see I can write. Okay, so the gate to bulk capacitance I can split two things. So one is gate to source, gate to drain because channel is formed. So uniformly distributed. So what is the actual oxide capacitance? WLCR. Since it is uniformly distributed, I can distribute for source and drain. Equally, I can distribute. So that means WL Cx by 2, WL Cx by 2. Is it understandable what I'm saying? Once the channel is formed, gate to bulk capacitance will be contributed by the gate to source and gate to drain. Since uniformly, I can approximate equally gate to source, gate to drain, because looking on gate to source, both are an equal number of charges. So I can split the capacitance like actual capacitance total is WLCR. So 50% I can assume for source, 50% assume for drain. So WLCR by 2. That is here due to channel is on triode region. Then already some more capacitance. What is overlap capacitance? W into C voltage. So you remember overlap capacitance also will be there. Okay, so when turn on gate to this capacitance plus this overlap capacitance. So CGS will be WL times R. So WL CX by 2 plus overlap. Similarly, CGD will be WL CX by plus overlap capacitance. Is it understandable? Okay, so now one more important point. Okay, in triode, that means when the transistor becomes on, the inversion layer acts as a shield between gate and bulb. Okay, that means it won't. Okay, so right. Okay, so it will become shield. So there won't be any capacitance between here to here. Only the capacitance between gate to and channel. Okay, that is mentioned here. Okay, so that's all about capacitance in triode region. Okay, so you can see I am mentioning the triode region. Okay, so you can see a triode region. CGS, you can see this is CGS, this is C. So CGS is equal to CGD. So what is the formula? Of WLCR plus 4 day capacitance. So that's what both are equal here. CGS and CGD are equal. Is it understandable? Any doubts here? What? Okay, so now we'll come to a very important saturation. So what will happen in saturation? What happened to the channel?
Pinch off.
Pink off. So pink off means whatever charge in drain, whatever charge at drain, what about the charge at source?
Charge at source is higher than drain.
Okay, good. So that means it is non-uniform. Charge distribution is non-uniform. That means more charge means more capacitance. Less charge means less capacitance. So you can see at the pink off point, at the drain terminal, due to pink off point, at the drain terminal, no charge. So what is the capacitance at the drain terminal? CGD. Previously,
Zero.
okay, let me write in triode region. Okay, let me write CGD. CGD. In triode region, what is the formula? Of WLCR plus overlay capacity.
Overlay.
Okay, so W into C overlay. What about CGS?
Half into double.
Same formula. Of
Same
WLCR
formula.
into C overlay. So now I am coming to saturation region. So saturation region due to pink off at drain terminal, no charge, no capacitance. So what can I write here?
WCOV.
WCO.
WCO, only that thing. Okay. Similarly, here also WCO infrared. What about CGS?
Both.
WCO right? But some term WLCR not fully. Okay, so that is called 2/3. You can see more. You can derive. Might have derived this formula in the device physics. Please look on it. So 2/3 WL plus. So but oxide capacitance won't be in the in drain region because channel is completely pinked up. Okay, so in oxide in saturation region, PGS is 2/3 WL CR plus 4 day. So that's what you can see. Saturation region, CGS is higher. What about the drain? Drain will become only overlap. And so CGD equal to only overlap. So you can get CGD will be WQ. So that's what. Okay, in triode region, CGS, CGD are equal. In saturation region, CGS is higher than CGD. Okay, in off condition, both CGS and CGD only the overlap capacity. Okay, so that's what this. So any doubts here? Oh, fine. Thank you. So now we discuss about different capacitance. Okay, so in off condition means give to bulk capacitance will be there. Okay, it's a series connection of C1, C2. Overlap capacitance will be there. Depletion capacitance will be there. In triode region, CGS and CGD are equal because charges are uniformly distributed, but always depletion capacitance will be there. In saturation region, gate to source will be higher than CGD. It is due to the pink off effect. Okay, fine. So now we'll do this simple problem. Okay, so maybe I will come to this problem later. Okay, I will cover this thing. If time permit, I will do this problem. Okay. So, but mass capacitance is clear. Any doubts here? Is
No,
it
sir.
fine for all? Okay. Thank you.
Yes, sir.
So now we'll come to small signal modeling. This is very important. That's what I want to quickly finish it. Okay. So all of you studied about small signal model. What is the small signal model? You might have studied in the BTech courses. What is the small signal modeling?
Small signal AC analysis.
Okay, so let's 1 minute. Yeah, just 1 minute. I will draw the curve ID. Okay, so, fine. So, ID VGS. How the curve will be looking like? It will be looking on this thing. After the threshold voltage, it will be on. So, fine. Am I correct? This curve? Don't mistake me. Fine. Now, what is the equation? ID equal to half mu n Cx W. So here every region will come. VGS less than VT, triode will be there, saturation will be there. Okay, when VGS become higher, it will become. When VGS is higher, what is the operating region?
Saturation.
Triode.
Huh?
Triode.
So
Triode.
here half means you can assume for this. Here saturation, here triode. Fine. So where you want to operate our transistor amplification?
Saturation.
Saturation. Okay, and let I am operating here. Okay, I will put a. Okay, I will put this color. Now this is a Q point. Fine. So I'm expanding the Q point. This is the point. Now looking from the Q point, I am applying a very small signal. Okay, del VGS. Very small signal. Fine. So looking from here, the line is looking linear. Am I right? Looking very small perspective, line is looking linear. Such that the variation in VGS is very small, very small signal. So that means I can operate amplifier in a linear region. That means applying very small signal, I can operate in a transistor when a linear. That means there won't be any non-linearity. Okay, so we are always interested in studying the behavior of an amplifier in a linear region. That means there won't be any non-linear distortion. Okay, that means we are applying, let's take some circuit gain. I am applying 2 millivolt, let's take gain is 10, 20 millivolt. If applying 5 millivolt, 50 millivolt. It is linear behavior. Am I correct? LTI system. I want to understand the behavior by operating in a LTI model. Okay, so it will happen such that when you apply very small signal, when you apply large signal, this linear behavior won't come. Distortion will come into picture. Okay, so gain is not we cannot define V out equal to A into Vin. Okay, it is only for a small signal, linear behavior. If you come into non-linear thing, so the non-linear term will come. So A square into 1 minus n. Some non-linear term will be there. I cannot exactly write, but non-linear term will come into picture. Okay, so we are always interested in studying the linear behavior. Okay, so for studying it, we need to model our transistor in small signal, applying the small signal, how the behavior of the transistor. So that modeling of the transistor for applying very small signal, it is called a small signal modeling. Okay, that means we are representing our transistor by applying the small signal. We are representing in terms of RLC component and with some current sources. That means we are converting active element in terms of some passive representation by applying the small signal. Is it understandable what I'm saying? So that's what is called the small signal. But with respect to the bias point. So what is the bias point? Q point. What is the bias point here? Anyone can say what is the bias point here? Y comma x. How can I write? How can I write at this point?
ID1 comma BGS1.
Yeah, ID1 comma. That means I'm operating the transistor with VGS1, fixed VGS1. So fixed VGS1, there is fixed ID. So in this bias condition, applying small signal. Very comparing the biasing value. This is a bias point. Okay, applying very small signal. What will happen to the behavior? That's all. With respect to the bias point. Fine. So that is called small signal. So once the bias point is fixed, okay, we can model the transistor using the small signal model. Okay, so that means apply certain bias voltage, then increment the very small signal, understand the behavior. Okay. Okay, so before going this thing, so what is a MOSFET? Applying the
Voltage
gate to
control.
source voltages, what it will change? What will happen? Gate to source voltages. What is the output? Current or voltage? Wherein the gate to source voltage?
ID current.
Current.
Current variation.
Yeah. So that's what. Varying the thing, current will vary. So we are applying del VGS, del ID. Small signal. Right? So what is the relation between current and voltage? Transconductance. Okay. So MOSFET we are applying the voltage, the output we are observing is current. So what is the relation between current and voltage? Transconductance. Output is current, input is voltage. Okay. So that parameter relating the change is called as transconductance. So I can represent GM into VGS. So VGS is the input. Okay, so the varying VGS, okay, will change the current. So what is the relation between current and, okay, so what is the relation between current and voltage? Transconductance. Right, so ID VGS. I hope you understand. This is I am saying not a DC perspective. Right, so DC perspective, what is the equation? Okay, so I am saying DC perspective, that means bias perspective. DC or bias. So what is the relation between ID and VGS? ID equal to half mu n CR the V by L VGS minus VTS whole square. Now I am saying coming AC perspective or small signal. Small signal means what? AC signal. Okay. Now I am getting small signal perspective. Okay. So now small signal means I am applying small signal. Low ID. Right. So I am observing. Okay. So I am applying low VGS. I am observing what is low ID. Am I correct? So let differentiate here. What is low ID by low VGS? What is this definition? We have studied
GM.
last class.
GM.
What is
GM.
GM?
GM.
So good. So let's assume del ID to a very small term. So del ID equal to GM into del VGS. Am I correct? Only small signal, small differential. So this is a thing. So this is a equation for the small signal model for GM. Relation between current and voltage in small signal thing. Right? So that's a thing. So I can write idea GM into VGS. I hope you understand. VGS means don't think like capital. It is a small signal. You can think like del VGS, or simply instead of capital thing, you can small signal. Okay, so small v, small g. It's not a DC. That's what I want to convey. Right. So that is this thing. Okay, I model as a current converter. So how the current will flow in NMOS? Drain to source. Drain terminal to source terminal, you put on current source. That's what you can see. This is voltage dependent current source. Am I correct? MOSFET operates as a voltage because applying the voltage current will vary. So that's a voltage dependent current. Fine. Okay. So now This is a ideal thing. But practically current is not constant in the MOSFET. So what is your formula? Instead of this thing, 1 plus lambda VDS will come. Right? So let me write. So what is ideally we are expecting? This current, ID versus VDS. But practically what happening? Current is not constant. Fine. So VDS, this is called as 1 plus lambda VDS effect. Fine. You can see this effect. How can you model this thing? Dou ID divided by dou VDS. What is dou ID by dou VDS here? 0. Am I correct? Ideally dou ID by VDS, but practically dou ID by dou VDS not equal to 0. So I can model this as some resistance. That resistance called the channel and modulation resistance. Okay, so you can see dou ID divided by, so I want to define the resistance. So dou VDS divided by dou ID. I can write 1 by dou ID by dou VDS. Okay, so we can get this formula. So what is ID? Oh, sorry. I want to write here. So what is ID of mu n? See, once again I'm saying I'm modeling the transistor in saturation region because now we come to amplifier. NMOS in saturation. Fine. Of mu n CR W by L VGS minus VTS whole square into 1 plus lambda VD. Fine. So here you can see after differentiation, this term is there. So and from this thing I can write, okay, so half mu n VGS meter I can write. So I can write half mu n P of W by L VGS minus VTS whole square equal to ID divided by 1 plus lambda VDS. So that's what you can see, ID divided by 1 plus lambda VDS and lambda. Okay, so you know if I assume lambda VDS is very, very small, I can approximate 1 by lambda ID. So R naught equal to 1 by lambda ID. What is lambda? Lambda is
1 by
channel and
PA, 1 by
modulation
PA.
curve. It is inversely proportional to 1 by L. Am I correct?
Yes, sir.
Lambda, what is a relation
sir.
between lambda and you know uh,
L
it is
minus.
also, if yearly voltage is high, lambda will be high. Okay, but it is inversely proportional to L. Fine. Okay, so now you can see ideally, okay, ideally you can see ideally R naught is infinite. But practically, due to channel and modulation, R naught is equal to some finite value. Okay, that means it limits the gain. You know, if you take gain expression, they are always proportional to the impedance, output impedance. Output impedance means some R naught. Okay, if R naught is finite, means gain is reduced. That means that R naught channel and modulation resistance will limit the gain because finite R naught. But ideally, we are expecting more thing. Okay, due to channel modulation, gain is reducing because there is some finite resistance. Okay, so that's a R naught effect. Okay, so the next thing is body effect and time 9:50. Okay, so this thing body effect I will take in next class. Okay, so no problem. I need to cover body effect and the final small signal model set. Okay, I will take in next class. So any doubts here? Stop recording.